Hi, welcome back. And I really gotta start changing up my intros or something. I don't want one of you clipping the start of every video with me just my hair growing slightly longer and me changing shirts, saying the same thing every time. Don't do it. Anyway, today we're gonna talk about symmetric matrices, and this is like the whole next portion of the class. Okay, so it's like we just left the projections portion, even though projections will still be important at later points in the course. Now we're moving on to the symmetric matrices portion. So we're going to spend kind of a lot of time studying symmetric matrices and special kinds of symmetric matrices. And so they are arguably the most important kind of matrices. They're also extremely nice. So the whole point of this will be that these are extremely nice and they're also important. And we'll see exactly how they're nice because we'll develop some of their properties today and over the coming lectures. Let me first give you a very natural example of where you might find symmetric matrices. And this has already come up on the homework, which is if you take a look at the adjacency matrix of a graph, right? So if you take any graph, which is just a collection of nodes and edges, and then I will assume that this is not a directed graph, so it's not like the PageRank example. So basically, if 1 is connected to 2, then 2 is connected to 1, right? So you have some graph like this. This is your graph G. Then you can take the adjacency matrix. We also talked about this in the Google PageRank lecture, and it appeared on your problem set. But the adjacency matrix, you just put a 1 if there's an edge between those two vertices and a 0 otherwise. I mean, you can even have loops here if you want. I shouldn't draw an arrow, though. You can even have a loop here, like an edge from 1 to 1. Then you would get something like this. 2 is connected to 1 and 3 and 4, but not to itself. 3 is connected to 4 and 2. And 4 is connected to 3 and 2. Have I done this correctly? No, I haven't done this correctly because 2 is also connected to 4. And 4 is not connected to itself. There we go. Okay, so in setting up this adjacency matrix, because if 1 shares an edge with 2, then 2 shares an edge with 1, this thing will be a symmetric matrix, which I haven't defined yet, I guess. But a symmetric matrix is just one that is equal to its transpose, right? So it sort of has symmetry along the main diagonal. You can think of it like that. So here's the definition. So it only works for square matrices because otherwise the matrix has no chance of being equal to its transpose. This is called symmetric. If A equals A transpose. So if you switch the rows with the columns, you get back the same matrix. Okay, so this is an example of a symmetric matrix. Of course, you don't need to have only 1 and 0 entries, so you can pick anything you want, 1 pi 3. But if you have 1 pi 3 in the first row, it must mean that the first column is also 1 pi 3. Right? You can sort of put anything you want along the diagonal. But once you have an entry here, like this is 0, then that forces this entry to be 0. Right? So this thing is symmetric. Its rows are equal to its columns. But most matrices are not symmetric, right? If I just pick, I'll pick the same matrix as in the notes. This is not symmetric because its rows are not equal to its columns. I guess I should be a little bit more specific. The ith row is not always equal to the ith column in this matrix. Okay, so what we'll build up to today is we'll build up to, and maybe we'll go a bit over, the spectral theorem. I think we'll get there today. Okay, so we're going to need to develop some facts about symmetric matrices. I don't know why I have so many pages here. There's nothing on them. But just recall that for a complex number, and every complex number looks like a plus bi, the conjugate is going to be, you denote it with a bar, and it just means you negate the imaginary part and you keep the real part. Okay, and If z is real, then of course z bar equals z. I mean, we already talked about this stuff. And also, taking conjugates has nice properties, like the conjugate of z times w. So if z and w are complex numbers, then the conjugate of z times w is the same thing as the conjugate of z times the conjugate of w. These things are elementary. You could prove them just by writing down the definitions. Okay, now we'll define if A is a matrix, could be any matrix actually, then the conjugate of A is the matrix A bar given by conjugating each entry. So this should be a complex matrix, potentially, given by conjugating each entry. Right, so now if I have a matrix with some potentially imaginary components, right, potentially real components, stuff like this, if this is A, then A bar is just you conjugate every entry. 1 minus I, negative 3I, 2 pi. Okay? Because when you conjugate a real number, you just get back the real number itself. So that's actually one way that you can tell if a matrix is real. Right? So A is going to be a real matrix if and only if it's equal to its conjugate. One way that you can detect whether a matrix is real or not is you conjugate it and you see if you get back what you started with. Okay. Now that we have this, it's going to be important in some of our proofs. Let's state the first result, which is, again, the first thing that says that symmetric matrices are nice. So if A is a real symmetric matrix, that means it's a symmetric matrix with real entries, then all eigenvalues of A are real. Okay, remember, we could take some very simple matrices and get, with real entries, and get complex eigenvalues. That was way back in lecture 2 or something. But if you have a symmetric matrix that has real entries, you're guaranteed not to have any complex eigenvalues, or complex non-real eigenvalues. All of the eigenvalues of a symmetric matrix are real. So let's prove this. Okay, so suppose that lambda is an eigenvalue. Right, then I need to show that lambda is real, but this means that there exists a non-zero vector x such that a times x equals lambda times x. That's just what it means to say that lambda is an eigenvalue. Okay, and we can conjugate both sides of this equation. So conjugating, right, because this just says that these two vectors are equal, so if I conjugate both sides, those two vectors are also equal. We get that A bar times X bar. Okay, so I've been drawing arrows on the top of my vectors, and now I want to draw a bar on top of an arrow. So I'll try to be careful with that my arrows look like arrows and my bars look like bars. This is equal to lambda bar times X bar. But remember that A is real, which means that A bar equals A. Right, so A times X bar equals lambda bar times X bar. Okay. This, all I've used is that A is real, by the way, right? So this would also be true even if A weren't symmetric. Because, and this is one way that you can sort of prove that the eigenvalues occur in conjugate pairs. You could also use just the characteristic polynomial, but notice that what this is saying is that if lambda is an eigenvalue, then lambda bar will be an eigenvalue. So here I haven't used that A is symmetric yet. Okay, now what we're going to do is we're going to take the transpose of this. So taking the transpose, right, now I'm going to use that it's symmetric. So what is the transpose? So to take the transpose of a product, you can take the product of the transposes in the opposite order. Right, so let me just first write down this. So this becomes x bar transpose A transpose, and this is just a vector, right? It's a scalar times a vector. So this is still lambda bar, but it's times x bar transpose. Right, which means that because A is symmetric, so this was because A is real, but now because A is symmetric, A transpose is just the same thing as A. So this is x bar transpose A equals lambda bar x bar transpose. Okay, so now what I'm going to do is I'm going to work with this equation and this equation. What I'm going to do is I'm going to multiply the top equation by x bar transpose on the left. Okay, so let's call this a star. So from star, we have x bar transpose times ax equals lambda x bar transpose x. Right, lambda is a scalar, so I can just pull it out. But now what I can do is I can multiply this equation on the right by x. So from double star, we have x bar transpose A, now multiplying on the left by x, equals lambda bar x bar transpose x. Right, so these two equations are almost exactly the same, except one has a lambda and one has a lambda bar. Right? Now, I can't yet conclude sort of what I want to conclude. So I know that these two are equal, right? Because they're both equal to the same thing. But it might still be the case that this thing is 0. If those things were 0, it wouldn't tell me anything about lambda. Right? So I guess let's put this in words. So this means that lambda x bar transpose x equals lambda bar x bar transpose x. But since x is not 0, since it was an eigenvector, this thing, x bar transpose x, is not equal to the zero scalar. Because, well, you can just do a computation to convince yourself, right? This means that lambda equals lambda bar, right? Because lambda times some non-zero number equals lambda bar times some non-zero number. You can just divide by that non-zero number. But this means that lambda is real. That's exactly what this means. Okay, so if you have a symmetric matrix, then because you can play around with these conjugates and these transposes, you can actually show that every eigenvalue has to be real, which is a really, really nice property of symmetric matrices, and it's not at all obvious, right? If I just hand you a matrix, it's not going to be clear whether or not all the eigenvalues are real, but it is true for symmetric matrices. Okay, and it's a very easy corollary of this, that also for symmetric matrices, all of the eigenvalues only have real entries as well. So this is really just a corollary. So if A is symmetric and real, then each eigenspace of A has a basis consisting of real eigenvectors. And again, if you forget, just go back in the notes. Very early on, we had a 2x2 matrix that was real, where the eigenvalues were I and minus I, and the eigenvectors were like 1i and 1 minus I, something like that. So for a general real matrix, you might have to take complex eigenvalues, and therefore you might have to take complex eigenvectors. But for a symmetric real matrix, you're guaranteed that the eigenvalues are real. And then from there, it's actually quite easy to see that the eigenvectors have to be real. Why is that? So if lambda is an eigenvalue, then we just saw that that means that lambda is real. And do it like this, lambda is in R. But then if you consider the eigenspace, this is just the null space of A minus lambda I. But now this is a real matrix, and this is a real matrix because lambda is real. And so this is just the null space of a real matrix. And we have an algorithm for finding the eigenvalues, finding the null space of a matrix. It involves row reduction and pivots and free variables. But at every step in that process, if you have a real matrix, you're never going to ever do any part of that process which would take you to a complex number. So, I mean, if I told you this at the beginning of the course, you would have probably believed me more. The null space of a real matrix has a basis of real eigenvectors. Or has a basis of real vectors. And that means that all of your eigenspaces have a basis of real eigenvectors. Okay, so two non-obvious facts about real symmetric matrices is that all the eigen stuff that you get is real, which is not in general true for any real matrix. Okay, we have another example, just to motivate the next result. I actually forgot about this example. So you can consider this matrix 1, -1, 0, -1, 2, -1, 0, -1, 1. And this is a 3x3 matrix, so you could either do it by hand or you could plug it into Julia or your favorite software to find that the eigenvalues of this matrix, they have to be real. They are 0, 1, and 3, because this is a symmetric matrix. Then you can find the bases for the eigenspaces. So I'll just call it the eigenvectors. Each of them has a one-dimensional eigenspace, and they're spanned by 1, 1, 1, that's the first one. 1, 0, -1, that's the second one. 1, -2, 1, that's the third one. Okay, and one thing that is true about these vectors is that if you take the dot product of any two of them, you get 0. So notice that each of these is orthogonal. These eigenvectors are orthogonal to one another. Right? In other words, like ui transpose uj is equal to 0 if I does not equal j. And you might think, oh, well, he rigged up a special symmetric matrix to make this happen. But if you pick any random symmetric matrix, this phenomenon will happen. So you should just choose your favorite symmetric matrix and then see that, okay, of course, if you have an eigenvalue with higher multiplicity, you could choose a different basis, right? Like if you had two-dimensional eigenspace, then you could choose either a basis where they're orthogonal or where they're not. But if you take basis vectors from the different eigenspaces, they will always be orthogonal. So I encourage you to do some experimentation with a computer algebra system. Type in a random symmetric matrix, look at the eigenvectors, and then check for yourself that when you take the dot product, you get 0 when you take vectors from different eigenspaces. That's the content of the next theorem, so we'll see why that's true. So here's the results. So two real eigenvectors from different eigenspaces of a symmetric matrix are mutually orthogonal, or just are orthogonal, because it's only two vectors here. All right, i.e., that is, if lambda 1 is different from lambda 2, so you choose two different eigenvectors, and x is in E lambda 1, and y is in E lambda 2, then x transpose y is equal to 0. Okay, so what's the proof? This is sort of just in some sense, a follow your nose kind of proof. So let's suppose that ax is equal to lambda 1x, and ay is equal to lambda 2y. So suppose, and x and y are non-zero. So suppose that I have two different eigenvectors from two different eigenspaces. Okay, well, at some point I need to use the fact that A is symmetric, which means that I should take a transpose somewhere. So let's take the transpose of this guy. So take the transpose. We'll get x transpose A transpose equals lambda 1 x transpose. Okay, now let's multiply this equation by y on the right. Again, you need to make sure that the sizes match, but A is n by n, A transpose is n by n, x transpose is 1 by n, so you can multiply by an n by 1 vector no matter what, right? So then we get x transpose A transpose y equals lambda 1 x transpose y. But A transpose is the same thing as A, because A is symmetric. Right, so this is equal to x transpose AY because A is symmetric. But now since y is an eigenvector of A, this is just lambda 2 x transpose y. And now again, we're in the same boat. We have this is equal to this, and that lambda 1 is not equal to lambda 2. That means that x transpose y must be 0. Right, so these two things together, and you add the fact that lambda 1 is not equal to lambda 2, imply that x transpose y equals 0, so x and y are orthogonal. Okay, so symmetric matrices are somehow, this fact that you can take the transpose and you get the same thing back is giving us a lot of nice properties. Like sort of an astonishingly large amount of nice properties just from the fact that it's symmetric. What do we get? The eigenvalues are real. The eigenspaces have real bases. And now what this is saying is that if you look at the different eigenspaces of this matrix, they're all perpendicular to one another. It's really pretty astounding. Right? So the picture of the eigenspaces of a symmetric matrix, it doesn't even need to be real, just of a symmetric matrix, is that if they're all lie at right angles to one another, so if this is like one eigenspace, in this case I've drawn it as one-dimensional, but maybe you have a two-dimensional eigenspace, but no matter what, they'll lie at right angles to one another. So the eigenspaces here are highly structured for a symmetric matrix. They have a really nice geometry to them. Okay, not only that, there's an even better fact, which is a thing that the notes say we might prove this later. I don't actually know if it's proved later in the notes or not. I'm not even sure if it's in Strang's book. It might be. It's definitely in like the 340 textbook, but of course you're not required to have taken 340 here. Let's just accept this as a fact. If A is a real symmetric matrix, and lambda is any eigenvalue, then the algebraic multiplicity of lambda is equal to the geometric multiplicity of lambda. Corollary of this, of course, is that A is diagonalizable. Okay, so in other words, if you have a symmetric matrix, all of the eigen stuff about it is as nice as possible. Every eigenvalue is real. All the eigenvectors are real. All the eigenspaces lie perpendicular to one another. And all the eigenspaces are as big as possible. You have as many eigenvectors as you want, and the eigenspaces lie at right angles. It's really, again, this is actually really kind of astounding that you get this much structure in the eigenspaces of a symmetric matrix. But it's true, and in fact, all the proofs are kind of elementary, except that we didn't prove this one, but we'll just accept this as a fact. And I believe this means that on your homework, you can also accept this as a fact, but I haven't looked at the problem set that's based on this material yet. So if I want something different than that, then I'll let you know via email. Okay, so the fact that the eigenspaces of a symmetric matrix lie perpendicular to one another means that you can take a basis of eigenvectors, well, at least if you choose them from different eigenspaces, and they'll be orthogonal to one another. But we can actually do even better by introducing an even nicer notion. It's not that different, to be honest, but let me introduce it. So let's just recall that a set of vectors is called, actually, technically we haven't made this definition yet. Okay, so a set of vectors U1, let's call them V's. V1, V2, up through, to be honest, this could be any K in Rn, is called orthogonal if every vector in the set is orthogonal to all the rest of the vectors in the set. So if Vi transpose Vj is equal to 0 for all I not equal to j. Okay, so I said we haven't seen this definition. Technically, we only defined what it meant for two vectors to be orthogonal and for two subspaces to be orthogonal. Now I'm saying a whole set is orthogonal if every pair of them, where they're different, are orthogonal to one another. Of course, most of the time, other than the zero vector, a vector is never orthogonal to itself. So that's why I had to say that I was not equal to j. Okay, but we're going to introduce an even nicer notion. So a set of vectors, and now I'm going to use the letters u, because I kind of want in your head you to associate the letter u with this notion and not just the orthogonal notion. This is called orthonormal if it is, first of all, orthogonal, and each ui has length 1. Okay, so orthogonal means perpendicular. Orthonormal means orthogonal plus unit length. So it's an even nicer set of vectors. They all lie at right angles to one another, and they all have unit length. So for example, the standard basis vectors, or the standard basis, say, of R3, but actually of any Rn, is orthonormal, is an orthonormal set. It's a set of orthonormal vectors, right? So an orthonormal set of vectors somehow looks just like the standard basis, right? A bunch of perpendicular vectors, all of length 1. Okay, now we'll call a matrix orthogonal if its columns are orthogonal. And we'll call a matrix orthonormal if its columns are orthonormal. Okay, so example, you can take, say, one of these permutation matrices that we learned about on problem set 2. This is an orthonormal matrix because its column vectors are orthogonal vectors of length 1. Right? If I change this to a 2, say, then it would only be orthogonal. It wouldn't be orthonormal. But since they all have length 1, it's an orthonormal matrix. Okay, and notice that being orthonormal is more special than being orthogonal, but it's not much harder to be orthonormal than orthogonal. If I give you an orthogonal set, you can easily make it orthonormal by just dividing through by the length of each vector. Right? That's actually just what I did when I went from 2, 0, 0, 0 to 1, 0, 0, 0. Right? I said, oh, here's an orthogonal matrix, but it's not hard to make it orthonormal or to produce a related orthonormal matrix by just scaling them all so that you have length 1. Right? So if you can ever get an orthogonal matrix, you can get an orthonormal matrix by just dividing through by the lengths of each vector. But what's not obvious is if I give you a subspace, if it always has an orthogonal basis. Right, so maybe let me write this down. So it's kind of clear that from an orthogonal set, we can easily get an orthonormal set. Just divide by the length. So like I said, orthonormal sets are special, but they're not that much more special than orthogonal sets. But what's not that obvious is, does every subspace have an orthogonal basis? Right? Or an equivalent question is, does every subspace have an orthonormal basis? Because if I have an orthogonal one, then I can produce an orthonormal one just by dividing. Okay, it's not that clear what the answer to this should be, but if we think about the geometry, right, and every subspace looks like some m-dimensional plane through the origin, and if I just give you an m-dimensional plane through the origin, you can set up like a coordinate system, it seems like, right? Again, throughout this entire class, I'm going to draw only one picture. It's this picture. Here's a subspace. But it seems like if I give you any subspace like this, you can just choose a coordinate system. Let's say this is one direction and this is the other direction. Make sure that they're at right angles to one another. And then if it was a three-dimensional subspace, I could choose like an XYZ. It seems like we should always be able to find an orthogonal basis for any subspace, since they all basically look like this, right? And that's true. So the answer is yes, and there's even an algorithm to do it. If I give you a basis, right, so if v1 through vk is a basis, then there's an algorithm, which is really not so hard to understand, but let's just accept that it exists for now. It's called the Gram-Schmidt algorithm, that produces, let's actually call it u1 through uk, an orthonormal basis of V. Okay, and actually, that algorithm actually uses just projections. You just subtract off projections. It's a thing that you could actually understand geometrically, and the algorithm is not so hard. But the point is that every subspace actually has an orthonormal basis, and you can compute it easily if you have a basis. You just run this algorithm, and it spits out an orthonormal basis. Okay, so let's also accept this. So let's accept this as a fact. In order to get the following result. So if A is a symmetric matrix, then A has n orthonormal eigenvectors. Okay, so what this is saying is this is sort of just building on top of all of the nice properties that we've seen about symmetric matrices already today. It's saying that A has enough eigenvectors, it has as many as it possibly can, n. They'll be linearly independent because orthogonal vectors are always linearly independent, by the way. Each of the eigenspaces is orthogonal to one another. We already saw that. But within each eigenspace, because for each eigenspace you can get an orthonormal basis of that eigenspace, also within each eigenspace you can get an orthonormal basis of eigenvectors. So each eigenspace you get an orthonormal basis of each one individually. But now, since we saw already that if you have different eigenvectors, then you're orthogonal to one another, then all these separate orthonormal bases will be orthonormal to one another. They'll be orthogonal to one another. And so you can just gather them all together into an orthonormal basis of Rn, actually. Okay, so that's basically the proof. I mean, it's written better in the notes slightly. The point is that we'll have a bunch of eigenvectors and a bunch of eigenvalues. Each of these will be real. Now, for each eigenspace, call it E lambda I, you know that it has the correct dimension, right? The dimension is equal to the algebraic multiplicity. And that means that if the algebraic multiplicity is equal to, actually maybe let's not use another letter. So then we can find a basis for this thing, ui1, ui2, and the last one will be I sub am of lambda I. Basically, all I'm saying is you can find a basis for this eigenspace, and then you can make it orthonormal. So we might as well assume that we can find an orthonormal basis by using the Gram-Schmidt algorithm. And so you do this for every single eigenspace. In the end, you'll have n eigenvectors because each one is equal to its algebraic multiplicity. And each of these is orthogonal to every one of the elements in the set. But by our previous result, is also orthogonal to every vector in all the other eigenspaces. So you throw these all together and you'll get n orthonormal eigenvectors of A. So just combine all these bases together. All these orthonormal bases of the E lambda i's together to get n orthonormal eigenvectors of A. Okay. So we can now state, I mean, essentially this, you could call this the spectral theorem. Actually, maybe not, because in this part of the lecture, I haven't talked about, I mean, in this statement, I never talked about the fact that the eigenvalues are real. But this is almost all of the spectral theorem. The spectral theorem just summarizes very succinctly all of the nice properties of symmetric matrices that we've seen today. So let's just state it. This is called the spectral theorem. Very important theorem. Very useful theorem. It says that if you have a real symmetric matrix, then A has a diagonalization. A equals Q lambda Q inverse. I've missed a result. That's okay. I can just bake it into this one. Equals Q lambda Q transpose. where lambda is real and diagonal, and Q is orthonormal. Okay, so there's actually only one part of this that I need to prove, and it's proved separately in the notes, but I can prove it here. Okay, well, first of all, we know that A is diagonalizable because it has n linearly independent eigenvectors, because all the algebraic multiplicities equal all the geometric multiplicities. So that says that it has a diagonalization. We know that lambda is real because we showed that every eigenvalue is a real eigenvalue. And we know that we can take Q to be orthonormal because we just said that you can get an n orthonormal eigenvectors. And since the Q is made up of the eigenvectors of A, we can choose them so that they're orthonormal. So everything here follows from what we said already, except this equality. Right, so the only thing to show is that Q inverse is the same thing as Q transpose. This is a very useful fact, so that's why it's stated separately in the notes. If you have an orthonormal matrix, its inverse is incredibly easy to write down. You just take the transpose. So how do we do this? Okay, so suppose that Q looks like this. Let's write its columns as U1 through UN, where these are orthonormal. Okay, the point is that Q transpose has the row vectors being these same vectors. Right, so I'll write it like this. I guess these are transposes, really. Now let's just multiply Q transpose times Q, see what we get. Right, then Q transpose times Q is equal to this matrix times this matrix. And how do you get the entries of this? What you do is you just take every row here and you dot it with every column here, and then that gives you the ijth entry of the matrix. Well, since the U's are orthonormal, if I dot U1 with U1, I will get 1, because that's the length squared of U1. If I dot U1 with U2, I'll get 0 because they're orthogonal. Right? What I'll get here is the length of U1 squared, and then I'll get U1 transpose U2, U1 transpose U3, U1 transpose UN. Right? And in the next column, I'll get U2 transpose U1. I'll get the length of U2 transpose, sorry, just the length of U2 squared, rather, U2 transpose U3. Right, the point is the entries of this matrix are all the U's dotted with one another. And when you dot a U with itself, you get 1 because they all have length 1. When you dot a U with a different U, you get 0 because they're orthogonal. And so this matrix just ends up being 1s along the diagonal, 0s everywhere else. That's the identity matrix. That shows that Q transpose is the same thing as the inverse of Q. Because if you multiply it by Q, you get the n by n identity matrix. Okay, so this spectral theorem is what we've been building up to the entire lecture so far. The eigenspaces of a symmetric matrix are so nice that you can write down a diagonalization like this. All real eigenvalues. The diagonalization matrix is orthonormal, which means that its inverse is its transpose, so it's very easy to find the transpose. Okay. And there's an example in the notes. I don't think it's actually worth me writing it down, though. It's just writing down the Q and the Q inverse for a specific symmetric matrix. Yeah, so you should take a look at that example. It's just going to be me writing numbers in a matrix on here, which I don't think is a useful use of time. Okay, so this spectral theorem is really the whole point of today's lecture to get to this point. But there is one last thing in the notes, which is not actually really anything new. It's just sort of a recall that diagonalizing a matrix is the same thing as describing the linear transformation as diagonal with respect to a different basis. Right, the point was that if you could write A as x lambda x inverse, then what x inverse does is it takes you to a different basis. It changes basis to a basis of eigenvectors of A. And once you have a bunch of eigenvectors, since they're eigenvectors, what A does is it just scales them. Right, so this part tells you that you switch to a basis of eigenvectors of A, then you scale each of the eigenvectors by the appropriate eigenvalue, because that's what A does to them. And then multiplying by x takes you back to the standard basis. So this says that if you want to know what A does, you switch basis to an eigenbasis, then you scale in each eigenvector direction of the correct eigenvalue, and then you switch back to the standard basis, and that's what A does to your vector. Well, if A is symmetric, it means that you can write A as q lambda q transpose, where now this is real and this is orthonormal. So from this perspective, what are you doing? What you're doing is you're just changing basis now to a very special basis, a special eigenbasis. This is not just any old basis, it's an orthonormal basis. In other words, in some sense, it looks just like the standard basis, right? It's a bunch of length 1 vectors that are sitting orthogonal to one another. So it's not quite a rotation because you can switch orientation. You can sort of switch the right-hand rules or whatever. But basically what you're doing is you're going from the standard basis and you're kind of like you're rotating to a different orthonormal basis. With respect to this orthonormal basis, the action of the matrix just scales, right? Because these are eigenvectors of the linear transformation. And then you're just rotating back to the standard basis. So again, this is actually not anything new. We already talked about thinking of diagonalization as a change of basis, or thinking about the linear transformation in a different basis, a very nice basis. But if you have a symmetric matrix, right, that's the whole point here. If this is symmetric, then the nice basis you get is even nicer than nice. It's an orthonormal basis of eigenvectors, which in general could never happen. Might not happen, right? In general, if you look at eigenspaces, now I'm going to draw the same picture but different. In general, if you look at eigenspaces, you might have one eigenspace that looks like this, and you might have one eigenspace that looks like this. That's not going to be perpendicular, and there's no way to choose a basis so that, an eigenbasis, if you take one vector from here and two vectors from here, such that they're all orthogonal to one another, because the blue line just isn't normal to the plane. So in general, there's no hope of doing this, but for a symmetric matrix, you can always choose an orthonormal basis so that your change of basis matrix is just kind of like a rotation of the standard basis. Okay, so this is nothing new. I think it's just to remind you of this geometric perspective, change of basis perspective on what diagonalization really is. And since symmetric matrices have incredibly nice diagonalizations, it means that you can do this process in an incredibly nice way. Okay, so next time we'll talk about semi-definite matrices, which is going to be a special class of symmetric matrices, even nicer symmetric matrices, and we'll develop some of their properties and see why they're so important. All right, see you then.